Okay, with that, we're going to go ahead and get started. Let's see here. So as we go through today, if you have any questions, send them in using Q&A. Question and answer box there. Go ahead and use that. Do not send it in via chat. I cannot see those chats very easily as we go through here today. And also just a warning, Spectrum's apparently doing some work on the internet connection around here somewhere. I have lost internet twice this morning. It usually comes back in a few seconds. So if you see a warning that the host has left the webinar, I will rejoin it hopefully within just a few seconds and be able to start things back up again. So apologies in advance in case that happens. So without further ado, we'll get started. We're talking about Wi-Fi, how it works, what it does, sort of more of a technical thing, not so much a product thing today. So we'll start with a little background on Zysel for those of you that are maybe new partners or are not that familiar with us. Zysel has been around for over 30 years now. We got started all the way back in 1989 making networking equipment. We've been doing that this entire time. We currently serve over 150 different markets, and we have over 100 million devices deployed out in the field. So that's it as far as the background goes. The company itself, our headquarters is in Taiwan. The US office, US operations, is based out of Anaheim, California. So that covers all of North America, including Canada, Mexico, and we handle here out of the Anaheim office. That is our warehouse, that is our marketing, that is our sales team, and that is our tech support. So on to Wi-Fi here. So we'll start with the Wi-Fi players. There's three names you've probably seen if you've been doing Wi-Fi for a while: IEEE, Wi-Fi Alliance, and the FCC. So they all have different roles that they play. IEEE is the group that puts together the standards for all different things when it comes to networking. So they're the ones that define how Wi-Fi is supposed to work. So that's why when you're looking at a Wi-Fi device, you will see it, say 802.11ax, 802.11ac, etc. So those are references to the IEEE standard. So when IEEE creates a standard for Wi-Fi, it will start with 802.11 in most cases. The Wi-Fi Alliance is a group of manufacturers and resellers of Wi-Fi equipment, and they help certify product compatibility. So this was a big problem back in the early days of Wi-Fi. Any of you that have been out there probably know when you're looking at standards and people are reading things, different people interpret things differently. And no matter how careful you are with your wording, there's always going to be somebody out there that has a different idea of how to do something, especially when it comes to actually designing and implementing technology. So because of that, there were some areas where Wi-Fi did not get, certain Wi-Fi products did not get along with other Wi-Fi products. A big case of this was the early Apple products. Some of the early Apple iPhones and iPads had connectivity issues because they didn't properly implement the standard. And a lot of vendors, including us, had to go through and modify our implementation to work around some of those errors. But the Wi-Fi Alliance is there, the setup certification, and they will certify that products will work with each other. So they've got a series of tests that they go through to verify that products are going to work. And you have to pass those tests in order to use the Wi-Fi Alliance logos. Now, Wi-Fi products do not have to have these logos, and in fact, most business class products do not bother with getting Wi-Fi certified. These days, it is very, very rare to encounter any sort of incompatibility between different vendors' products, regardless of whether the Wi-Fi Alliance logo is there or not. For the most part these days, the Wi-Fi certified logo is primarily used on consumer-grade equipment. The other thing the Wi-Fi Alliance has done fairly recently is they have rebranded Wi-Fi. So instead of referring to products as 11N, 11AC, etc., the Wi-Fi Alliance has decided to rebrand Wi-Fi as Wi-Fi 4, Wi-Fi 5, Wi-Fi 6, and they've done that to make it easier for consumers to know which is the latest, most up-to-date standard that the products are using. And then after that is the federal government with the FCC. They're the ones who monitor and enforce rules as it comes to using radio waves. So they're going to be out there. They determine which frequencies Wi-Fi devices can use. They determine what's the maximum amount of power you can use, and they determine things like, how much band edge bleed over there is, et cetera, things like that. So all three of these play an important role when it comes to Wi-Fi products. So we'll talk a little bit here about radio waves. So Wi-Fi is using radio waves. So just some general things: as frequency goes up, the easier it is to cram more data onto it. So in general, higher frequencies give you higher data rates. The downside is, as frequency goes up, the range goes down. So for those of you that are old like me, you probably remember the early days of cordless phones versus, cordless phones today. And if you're young, you probably maybe have never even seen a cordless phone. You just use a mobile phone. But in the early days of cordless phones, they used the 900 megahertz spectrum. It's a small spectrum, but those cordless phones, you could get on and be having a conversation with your aunt or your best friend. You could walk outside, you could walk through the yard, you might even be able to walk over to your neighbor's house and still maintain a phone call. The problem was, as more and more people got cordless phones, is there wasn't enough radio bandwidth available for those users. So you ended up in situations where people started getting interference from each other. They were able to listen to each other's calls because they were using the same frequencies. So you saw in the late 80s, early 90s, a move to 2.4 gigahertz. 2.4 gigahertz expanded the amount of spectrum, so you could have more phone users talking on the phone before there was any sort of interference. And because the frequency was higher, the call quality sounded better because you were able to cram more detail into those radio waves. The downside was you could no longer go so far with your phone. In fact, especially in some of these bigger houses, you probably couldn't even go out into your backyard and still maintain a call. Again, in areas where you have a lot of users like apartment buildings and condos, you still had more users than you had available bandwidth. So then in the mid 90s, you saw really a big push to 5 gigahertz cordless phones. Again, the big push with this was better sound quality, better security, but the range got even less. So these days, for some of these bigger houses, you can't even go all the way around your house and always be able to maintain a good call without using some sort of booster. It's the exact same thing with Wi-Fi. Wi-Fi is using the same 2.4 and 5 gigahertz spectrum that cordless phones also use. So when we talk about radio waves, we measure the power in something called dB or dBm. And this is what you will primarily see when you look at data sheets of business class access points. When you're looking at more consumer-focused products, you will often see the power output given as milliwatts instead. Now, dBm is nice to use because it works with all of the various formulas you might be using to determine range, signal loss, things like that. You can take the dBm output power of your chip. You can add the dBi, the increase that your antenna gives. You can subtract out dBi losses due to cables and connectors and be able to easily calculate the total amount of power that you have radiated down to the antennas. You can't do that with milliwatts. So if you're ever doing anything or thing where you're adding different things together, different components, you're always going to have to use dBm. Now, dBm is interesting because for every 3 dBm increase you have, you double your milliwatt power output. So that's why consumer products tend to focus on milliwatt power, because small changes to the overall output power seem much, much bigger than they really are as far as practical terms go in milliwatts. So going from 20 to 23 dBm doesn't sound like a lot, but if you convert that to milliwatts, you can say, hey, we're double the power. We've got 200 milliwatts versus our 20 dB competition, who's only at 100 milliwatts. We've got double the range, but that's the trick. It doesn't really double the range. Range probably more closely matches percentage-wise to the dBm, although neither of those is really accurate when it comes to calculating range. So something that people tend to overlook when they look at Wi-Fi products and when it comes to performance and analysis is signal to noise ratio. But this is actually probably the most important thing it comes to when we are talking about quality of a connection and the maximum speed you can get to. So signal to noise ratio is basically a ratio of the signal, which is what you want to hear, that Wi-Fi signal you want to hear, versus any other sort of RF noise that might be interfering with it. So you get other RF because this 2.4 and 5 gigahertz are unlicensed spectrum. So just about any device that doesn't use wires, that uses some form of wireless communication, is using 2.4 or 5 gigahertz to do that communication. So Bluetooth headphones, cordless mice, as we were talking about before, cordless phones, et cetera, et cetera, et cetera. And on top of that, you also get noise being put out by maybe industrial equipment. You know, there's a bad connection in the air conditioner, so it's putting out RF noise. Microwaves put out RF noise. And just other people's access points, other people's wireless devices that you know, that you don't want to be talking at the same time. So all of those create the noise. So the better your signal to noise ratio, the easier it is for your device to hear what it needs to hear, so you can negotiate faster data rates than you would otherwise. So as sort of an analogy to that, you know, it would be if you and I are having a conversation, if we're just sitting in a small office, just the two of us, there's a really good signal to noise ratio when we're talking. The signal is our voices talking to each other. And again, the noise is any other noise we don't want to hear. Alternately, you try to have that same conversation in a bar at, you know, 11:30 at night on a Friday. You've got music, you've got other people talking, you've got a high level of noise, and you're not going to be able to communicate as smoothly, and you're going to have to probably get closer to each other to be able to hear each other. You may have to raise your voice, or in this case, you know, raise your Wi-Fi signal to be able to communicate with each other. And then the other thing to talk about here briefly is attenuation, basically how much the signal degrades based on business. So it changes based, or not business, distance. So the farther a signal goes, the more it's going to degrade. Also, it matters what sort of medium the signal is passing through. You know, a simple drywall wall is going to degrade the signal, but a concrete wall is going to degrade the signal even more. So that's your attenuation. And it also applies to open air. A lot of the calculators you'll find out on the internet, which help you calculate the distance of a connection, generally assume low humidity air. The problem is water absorbs Wi-Fi. So you may see a difference as far as range goes, you know, in the California desert versus in a Florida swamp, for instance. So you're going to have a difference there simply because the air itself has more water, which is attenuating the signal more. And this also happens to people sometimes when it comes to providing outdoor networks. You will go out, you'll do your site survey, you'll set everything up, and everything works perfectly fine. But then the weather changes. Maybe it gets more humid, maybe you get rain or snow, and suddenly those connections that were working great don't work as well anymore. So if you're providing outdoor coverage, if you're providing WISP type services, that's something you also have to keep in mind is not only is the signal good today, is the signal going to be good enough when the weather changes, when the circumstances are different, even if the distances are the same and the mounting points remain the same. So this formula up here is the formula you use to calculate what sort of distance you can get, right? So you take the distance here, multiply it by this, take the frequency you're using, multiply it by this, add 92.45, and that's going to tell you how much loss you're going to get over that distance. So then you subtract that from your radiated output power from the antennas, and that's telling you how far the signal is going to go. So as you can see, it's a lot more complicated than just looking at the dBm or just looking at milliwatt to try to determine based on that how much distance you're going to get. For those of you where this is important, which a lot of times is your outdoor point-to-point VARs who are doing that sort of thing, there are calculators on the internet that will help you out with that. And I don't really talk about it today, but there's other things for outdoors that you need to keep in mind, things like Fresnel zones. Basically, Wi-Fi signal, these radio waves, don't travel in a straight line. These bounce up and down and these spread out over an area called the Fresnel zone. So even though visually you've got a straight, pure line of sight, you still may have obstructions that you wouldn't think would be obstructions. And again, there are tools out there that will help you with that. There are some that are integrated with things such as Google Earth to be able to get topographical information, to be able to get and recognize trees and buildings and things like that that may be causing you. Anyway, We're not talking about that today. So this is just showing you here on the chart here, an idea of what sort of loss you may be able to expect from different things. A key one here shows, a glass window is going to get you approximately 3 dB of loss. However, a lot of commercial buildings have metal tints applied to them designed to keep out infrared, to keep out UV, to keep out light in some cases, and those will also affect your Wi-Fi. So you could go from a 3 dB loss, which is a power-wise loss, essentially having your power output, to up to an 8 dB loss. So a huge difference in whether or not that window is treated or not. But just in general, the thicker and denser an object is, the more it is going to attenuate the signal. So let's start talking a little bit here about Wi-Fi range in the real world. As we mentioned before, you can use that formula to sort of calculate based on paper and theoretical what things are going to do. But realistically, in the real world, Wi-Fi range is determined by a whole bunch of different factors. The signal strength, the signal to noise ratio, attenuation, the frequency you're using, all of those things. And things like background noise is something, that today may be one thing, tomorrow may be something else. But one thing we need to keep in mind is that Wi-Fi communication is two-way. So this is really important, and this is something people tend to forget from time to time. A lot of times people spend a lot of time focusing on the output power of their access point, right? Is it 100 milliwatts? Is it 200 milliwatts, 500 milliwatts? Theoretically, we could get up to 4 watts of radiated output power for an outdoor AP. But the problem is the device that's connecting to that access point is often significantly lower power. So you're talking here a difference from a 500 milliwatt AP connecting to something that may be only 25 milliwatt. I'm not sure the current model of iPhone, but just a few generations ago, an iPhone was putting out less than 25 milliwatts of power. So this is really important to keep this in mind. It doesn't matter if your device can see the access point and the signal it's sending. If the access point cannot hear the device for it to request information, for it to confirm its received packets. So even if you're streaming something or downloading a file off an FTP, which is primarily going to be data coming from the access point to the end device, the end device still needs to communicate back to the AP to let it know it's received the data that's been sent, it passed the checksum, the data is good, it's okay to move on to the next packet. And if you can't do that, your Wi-Fi doesn't work. And this is one of the biggest causes of one of those complaints we get from people, which is, oh, my Wi-Fi sucks. I'm looking at my phone shows I've got 3 bars of signal, but my internet's not working, or my internet is barely working. And the reason for that is because your phone, that signal strength indicator on your phone or on your laptop or on your tablet, it's telling you how well or how strong that signal is coming from your access point. It doesn't know if the signal is getting back to the AP. So that's what's causing the performance issue. You've got a good, strong signal from the AP. The problem is the AP doesn't have a good, strong signal back from that mobile device. So that runs into those situations where, people are like, it says I've got good Wi-Fi, why is it not working? And very often that's the reason. The signal is not getting back to the access point. So some other RF behavior things to talk about. So, one of the big challenges we have with Wi-Fi is we're sending out these radio waves, but they're invisible. We can't see them. It makes it hard to troubleshoot. It makes it hard to know what is going on. There are some tools out there that'll help you. There's software you can buy that helps you map and create heat maps of where Wi-Fi is, what your noise ratios are. There's various tools out there that will, scan the environment and you can walk around with. But even then, it's difficult and it's only in the time being. It takes time. You've got to walk around. You've got to go different places and see what the readings are. So it's a challenge. So some of the things here is just, how it works. So here's your AP, or I guess in this case, this is your laptop here. For some reason, I apologize, the slides got it reversed. Generally, when we're talking, we use the AP as the transmitter. But either way, in this case, a laptop is transmitting RF signal to try to get back to this access point over here. So that signal radiates out generally in a circular pattern. and hits various objects. And depending on those objects, different things can happen. So one of the things that happens is the signal can pass through something like a wall. It will get attenuated. In this case, we're calling it by diffraction, so that will weaken the signal as it goes through here. Simultaneously, the signal is going out in this direction. It can hit the wall, it reflect off of that wall. It can hit the wall and then scatter into multiple different ripples, I guess you might want to call it. Signals can also wrap around objects. It's very similar to the waves you see in a pond. You throw a rock in there, it generates out the wave that radiates out in a 360-degree pattern. And if you watch those waves as they interact with other objects, you will see much of the same behavior. In fact, you'll see pretty much all of the same behavior, except for the ability of a water wave to pass through a solid object. Another challenge we run into comes down to what we would call co-channel interference. So that's when two or more devices try to transmit at the same time on the same channel. It causes interference. Now, we normally, when we're talking about co-channel interference, if you've ever been to any of my other webinars, we're generally talking about interference from devices on different access points, things like that. But you also run into issues with devices on the same network connecting to the same access point. And that's because all the way back in the 90s, when 802.11 was first built, people weren't doing like they're doing today. They weren't streaming things. It was just very light data. There wasn't a lot of bandwidth available. There wasn't a lot of airtime available. So they decided that rather than create a method where the AP coordinates with each of the different connected devices and determines whose turn it is to broadcast, instead they would use this formula that you see up there on your screen. And it's really basic. If your device wants to transmit something, it then, what they call here, senses the medium. Basically, it listens and says, hey, is anybody else transmitting anything? If the answer is no one is transmitting anything, then you're given the okay to go ahead and transmit your data. If it determines that somebody else is already transmitting something, it then backs off a random period of time and starts the process over again until there is an opportunity where it can listen and then determine to transmit. And that worked well back in the old days. But now we've got so many wireless devices and so much data being sent, you run into situations here where two or more devices connecting to the same access point are going to stop, are going to need to send some data. They're going to listen. They're going to, both of them will see, hey, no one's transmitting, and both will decide to transmit at the same time, which then basically causes a collision and causes those packets to be dropped. One of the main causes of it is what's called the hit and none problem. So on one hand, you can have a lot of devices, and as you add more and more devices, it's going to become more and more likely that two or more devices will decide to transmit at the same time, causing issues. But it can also be caused due to the fact that the coverage area isn't necessarily overlapping. So in this slide here, here's our access point. The blue area is the area it's able to hear client devices from. This is its coverage area. However, the client devices have a much lower range. So when this laptop is all the way over here on this edge of the coverage area, this laptop is over here, you can see the access point is able to hear both of them. However, they aren't able to hear each other. So when this device is transmitting and this device listens to say, hey, is anybody currently transmitting right now? It can't hear this one. So it will say, okay, good, it's clear, it's my turn to transmit. And then the AP is going to be hearing both of them. It'll get confused. The packets are going to get dropped. So this method of determining, whose turn it is to broadcast and these issues has basically never been fixed up until Wi-Fi 6. So if you're using 11AC, 11N, 11AC wave 2, you're still using this old ancient way of determining whose turn it is to use and transmit data. So because that has largely been fixed with Wi-Fi 6, it's one of the reasons why Wi-Fi 6 is great in denser environments, because it's more able to, better able to use the available airtime without issues. And we'll talk more about Wi-Fi 6 a little bit later. Another thing I want to talk about here is data rate versus throughput. Now, These words can be used many different ways. I am using them very specific ways that I find most closely match with sort of real world usage out there, especially with end users. So data rate is what you're going to see advertised on data sheets, on Amazon listings, etc. And that's basically the total amount of data that's being transmitted from the access point to a mobile device, or the theoretical maximum that they can get up to. So you will also see this term on data sheets, sometimes called the physical rate or called the link rate. But that's what everybody is going to advertise, because that's how networking has been done and advertised since the very, very earliest days of wired connections. The problem you run into is that most users are looking at what I'm going to call throughput. So throughput isn't measuring the total data sent between the AP and the device. It's measuring the total amount of very specific data that it sends out. So for instance, if you go to speedtest.net, right, they'll take a file and they'll transmit that file to you. And then you'll look at it over time and you're able to determine how fast that data came in. The challenge we run, and that worked great in the days of wired connections. It doesn't work as well when it comes to Wi-Fi, because Wi-Fi has a bunch of additional overhead that makes Wi-Fi work and makes Wi-Fi possible, right? We're using radio waves in this dirty environment on these shared frequencies where there's all sorts of other things that can be putting out RF at the same time. So you have to put this extra protocol overhead on top of the data that you actually want to send, which added together gets you your total data rate. But when people test throughput, it's not looking at that extra data that gets added on that makes Wi-Fi work. So in Ethernet, you know, it's almost entirely the data you want to send is included in the data rate. Whereas with Wi-Fi, you've got all this other stuff going on at the same time on top of the data you want to send. So because of that, if you do something like speedtest.net, you know, you're going to see a throughput hit that's pretty significant. Depending on the situation, it can be up to a 60% difference between the advertised data rate and the maximum throughput you're going to be able to see doing some sort of speed test, because that's not measuring this extra data that's there. I hope that makes sense. I always have a little difficulty here trying to explain this. But this is something that results in a lot of complaints. You know, you can go to Amazon, pull up any wireless router or access point, and you will see plenty of people complaining, hey, this product is advertised as, you know, 300 megabits, 900 megabits, gigabit, whatever. But when I do speed test, it's nowhere close to that. These people are lying to me. It's not really a lie. It's just not understanding that these two things are measuring different amounts, different data over time, essentially. And of course, it also doesn't take into account a lot of the other issues that may be affecting things. You may have a weak signal. There may be interference. It may be that while your router is capable of broadcasting a 1.5 gigabit signal, your laptop, the wireless chip that's in there, isn't capable of being able to achieve those speeds. So there's a bunch of additional stuff on top of this that can also degrade performance when somebody does a speed test versus what is advertised on the data sheet. So let's talk about increasing speed. Now, I'm not talking about what you would do out in the field or you as an end user. I'm talking about how Wi-Fi itself, how we keep getting these faster speeds with each new standard. So there's three main ways that speed has been increased over the years. The first one is increasing the encoding. So QAM is a measurement, 64-bit QAM, 256-bit QAM, et cetera. So as time has gone on, and as chips become more powerful at the same level of power usage, they've been able to increase the QAM that's being used for encoding so they can fit more data into the same amount of available airtime. So 11N used 64-bit QAM, 11AC introduced 256-bit QAM, and Wi-Fi 6, 11AX is up to 1024 QAM at this point. So some big differences there. The next thing is spatial streams. And we'll talk a little bit more about spatial streams, but basically it's how many streams of data can be sent at a time. Original 11B, 11N products were only capable of transmitting one stream of data. Newer products are capable of transmitting 2, 3, 4, maybe even more streams simultaneously. And then just the bandwidth that's available to be used. So we'll start by talking about bandwidth. So we'll sort of go through these bullet points in reverse order. So the 2.4 gigahertz spectrum is only roughly around 60 megahertz of spectrum that's able to be used. Now, if you look at your, log into your router or your access point, you look at channels, in the US, we'll see 11 channels available to choose from. In Europe and some other places, you may see up to 13 channels available for use. The problem we run into is these channels, as originally defined, are really, really small. I think it's, so the challenge is, though, that the channels as actually used are 20 megahertz in size versus, I think, about 5 megahertz per defined channel. So that caused a lot of issues in the 2.4 days, because you put one device on channel 1, you put another device on channel 2, and you go, look, they don't overlap, we're free. But no, they were interfering with each other because 2 dramatically overlaps with channel 1. It also overlaps with channel 3. It also overlaps with channel 4, overlaps with channel 5, and overlaps with channel 6. So this caused a lot of confusion for people because they didn't understand what was going on. So realistically, on the 2.4 gigahertz spectrum, you had 3 different channels you could use that would not cause interference with any other wireless devices. But 11N came along and they said, hey, let's make this faster. We can double the speed if we double the bandwidth each device is using. So instead of using a 20 megahertz channel, let's use a 40 megahertz channel. We've instantly doubled the speed of our product. So while those other guys are saying, they're 54, we can claim we're at 108 megabits, which is absolutely true. The problem is, again, 2.4 only has 60 megahertz total spectrum available here in North America. So realistically, you can only have one device operating using a 40 megahertz channel. And as soon as you add a second device, whether it's a 20 or a 40 megahertz device, it's going to cause overlap and you're going to start having interference issues. So not only is this going to cause problems in something like an apartment or condo building, but even in homes, a lot of times, you can be getting interference from your next door neighbor because Wi-Fi signals can travel really far. And even if they're not strong enough for you to connect to them, they may be strong enough to cause interference. So that's why you saw a big push to 5 gigahertz. For a while there, they tried to produce devices that only had 5 gigahertz, but there was enough, client devices that only did 2.4. But so you ran into the situation where eventually the entire market moved to dual radio routers, dual radio access points, where everything these days has 2 radios, one 2.4 and one 5. So 5 opens up a huge amount of spectrum for us that wasn't available before. Now, when we're talking 20 megahertz channels, we've got over 25 channels you can use without causing interference. So this is fantastic, right, for apartments and condos and office buildings and things like that, where you have a lot of access points being used or a lot of devices being used. You now no longer have to worry about trying to manage those channels and make sure they don't overlap with each other. Or at least that's the theory. So the first thing I want to address here is you'll notice in the middle of this chart, we've got it highlighted in orange in the word Dfs channels. So this part of spectrum used to be licensed spectrum. When the FCC decided to move this over from licensed spectrum to unlicensed spectrum that everybody can use, the people who were already using this spectrum said, hey, wait a minute, we've been using this for decades. Now you're going to cause interference with us and you're going to cause issues with these applications that we've been using for decades. The most common being radars, whether it be weather radar or airport radars. So the FCC came along and said, well, we'll define these as DFS. I think it's dynamic frequency selection. And basically what happens is, in order for a Wi-Fi device to use one of these channels, first, it has to stop and listen to see if that channel is already in use. And I want to say that it has to wait 30 seconds. I could be wrong on that, but I think it has to listen to at least 30 seconds before it can start transmitting. So you may run into a situation, you tell your access point, hey, use this DFS channel. It listens, it's already in use, so it never turns on the AP, so no one gets to connect to it. The other thing that runs into here is your access point has to always be listening. And if it determines that there's a legacy device now using that channel, it has to stop using that channel. So that can cause people to get disconnects, right? And the access points aren't perfect. So it may be legit that there maybe is somebody a legacy device. It may just be a source of interference from something else, a piece of industrial equipment. But it's close enough that to the access point, it looks like it could be a legacy device, so it'll kick you off. So that's one of the challenges you run into, is that if you're using DFS channels, there's always the chance that you're going to be facing disconnects or being down for periods of time because your access point is determining another legacy device in the area is using that. I don't know where it is where you are, but over here we've got all sorts of weather radars from different TV stations. We've got seems like an airport on every other corner. So those cause some sort of issues. The other big problem with it is to get DFS certified, it can add up to 6 months to the certification process of a new product. And obviously, a lot of vendors want to be first to market. There's a lot of benefit to being the first or one of the first guys to be selling a new product using some new technology. So because of that, a lot of consumer equipment doesn't support DFS. The majority probably does. And a lot of times what happens is they'll launch the product without DFS support. And then through a software patch or a firmware update, they will add the support once it gets certified. But some products never get that DFS support. So if you're in a situation such as a hotel or maybe even in an office where people are allowed to bring their own device, you may run into situations where that device that's been brought doesn't support DFS channels. So if you're using DFS channels, that user is going to complain they can't get on the network. Or alternately, if you do have, they are able to get on some of the APs, but not others. So you'll get complaints from people saying, hey, we're using a voice application on the user's cellular phone. So it's voice over Wi-Fi. They're using their own cellular phone, or they're using their own tablet. And Bob and Steve over there, keep getting thrown off. They're not roaming properly. It works great at their desk, but if they come into the meeting room, it doesn't work. And very often the issue is, the APs in some of the building are not using DFS. The APs in other parts of the building are using DFS. So it's causing issues as those users are unable to roam. So it's something to keep in mind. And it's something to definitely play with if you're troubleshooting issues with users being disconnected or having roaming problems, is check. Am I using DFS channels? Am I not using DFS channels? There's pros and cons of doing it either way, right? You don't use DFS channels and you've now solved these issues with, users bringing their own device that may not support DFS. But on the other hand, if you're not using those DFS channels, you are handicapping yourself and dramatically reducing the number of channels that you can use. You may be increasing the risk of interference between access points or between devices. So that's one problem. The next thing is, again, we were talking about originally, how do we increase speed? And the way we do that, right, is we increase the amount of bandwidth that we're using. So while with 20 megahertz channels, you have something like 9 non-DFS channels that you can use. If you go up to 40 megahertz channels, you've now dropped that down to just 4. You've now only got 4 channels that your devices can be using. Before you start having to worry about interference between APs and being careful with channel planning and things like that. Obviously, if you use DFS, it's not quite as bad. But again, people said, hey, wait a minute, we want faster speeds. We need to advertise faster. Why are we just using 40 megahertz channels? I mean, sure, 2.4 can only use that, but what about 5 gigahertz? We've got all this spectrum. Let's double that. We can use 80 megahertz channels, and now we can claim to have doubled the speed again or quadrupled it from the original speed, right? So, but now you've only got 2 non-DFS channels that can be used before you start encountering interference. And that still wasn't good enough. So 11AC, Wave 2, 11AX use 160 gigahertz channels, massive increases to your speed. But now you have to use DFS channels. There's no way around it in order to get this much bandwidth. So something to keep in mind there, as we increase speed, you run into these issues. And most devices by default are going to be using the widest possible channel that these support out of the box. So especially on deployments in office buildings and hotels and things like that, it makes sense to go in there and reduce the channels down to 80 or 40 megahertz channels, so you're reducing the chance of interference between your access points. Okay, so that's it for bandwidth. Now let's talk about spatial streams. So as we talked about before, the signal essentially radiates out as a wave. It's a nice circular wave, but when it hits things, it can bounce off of them. So back in the 11A and 11G days, that was something horrible that we called multipath. So what happens is you send out one signal here. As it radiates out, it starts hitting things. So the signal that radiates out straight gets to your receiver device first, but then the signal is also hitting different pieces of furniture. It's hitting the walls, it's bouncing off of them. So they're all coming in. And because they're each following paths that are different lengths, they're arriving here at slightly different times. Basically, it's creating an echo effect, right? So if you've ever been in, a room with poor acoustics, you know how annoying echoes can be. And that's essentially what it is. The real world has poor Wi-Fi acoustics. And that caused all sorts of issues for us. Luckily, somebody smarter than me came along, and at least one of those people works at Zysel, and realized that you could take this multipath and turn it from a problem into a benefit. So basically, through technology, we're able to take advantage of these multiple paths a signal can travel, and we can send different data on those different paths. So that's where we get, multipath becomes MIMO, multiple in, multiple out. And the way it works roughly is you have different antennas in your device. Those antennas are physically spaced apart. On the receiving device, there are multiple antennas. And because we know how far apart these antennas are, we can use those to listen to different data streams, and we can take advantage of this echo effect and do some fancy stuff to basically allow us to isolate these different echoes. So what we can do is we can have one antenna send one stream, and a second antenna send a completely different stream, same RF channel. And then over here on your client device, it can hear each of those individual streams and then combine them together. So, 11 AC was 150 megahertz per stream. So this one, you've got two antennas that are able to transmit, each 150 megabits. So you get a 300 megabit connection over here. So that's what we call MIMO. Later on with 11 AC, I want to say wave 2, we added something that we now call multi-user MIMO. Same basic technology, but the difference is instead of both streams going to the same end device, we can now use different streams to go to different devices. So your access point can transmit data at 150 megabits to one user. At the same time, it's sending 150 megabits per second to another user. So this is what we call multi-user MIMO. So basically, you add those spatial streams together to get the total speed that you're up to. So when you're looking at data sheets, you will normally see the speeds, especially on business class products, instead of saying, 900 megabits or 300 megabits, you'll generally see 2 by 2, 3 by 3, et cetera, et cetera. And that's just telling you the spatial stream. So, by knowing the spatial streams and by knowing if the device is 11N or 11AC, et cetera, you're able to know what the maximum speed is that you can, in theory, achieve. So simple enough, you see 2 by 2. The first number is how many streams your device is capable of transmitting. The second number is how many streams your device is capable of being able to simultaneously process when you're listening. So most devices on the AP side of things, you will see the same number. You will see 2 by 2, 3 by 3, 4 by 4. However, on client devices, that's often not the case. So what you will often see in client devices is you can receive more streams than you can transmit. So you may see something like 1 by 2. Your device can hear two different spatial streams and combine them together. But when it transmits back to the access point, it can only use one spatial stream. So that's very common to see 1x2 or a 2x3 on client devices, sometimes even a 1x3. The one exception to this is largely generally going to be Cisco. Cisco plays some technical games here with how they denote their spatial streams. So what you'll often see on Cisco access point or on data sheets and stuff like that is you will see like a 4x4, a colon, and then another number. So instead of seeing two numbers, you're going to see three numbers. So what that's telling you is if you see a 4x4:3 is you've got four antennas that can transmit, four antennas that can receive, but you can only actually use three of them at any one time. Right, so realistically from a performance perspective, a 4x4:3 is the same as a 3x3. So why do they do it that way? One, obviously, if you don't understand these numbers, you say, hey, it's a bigger number, it must be better. If there is some benefit theoretically when it comes to dealing with, like RF noise and things like that. You can choose to use the three best antennas for listening, the three best antennas for transmitting, and there may be a tiny improvement because of that. So combining this all together, here we go, right? So we've got a bunch of columns here. Here's how many spatial streams you use. Here's what your modulation type is. So the modulation type that you're going to get is obviously depending on the standard that you're using, but it also depends on the RF environment. Basically, if you have a device trying to use 256 QAM and it's losing information, it's not able to hear the information coming through, the devices will automatically drop down to a lower QAM to sort of solve those issues. And then, how much bandwidth you are using, 20, 40, 80, or 60. So you have to go through these and combine them together to find out what realistically is the maximum data rate that you can achieve. Right, so if you've got a two spatial streams, okay, it's one of these. In theory, it would be 256 QAM, but maybe you've got some RF noise, you've got some interference. So it'll drop down to 64 QAM. And you're using 80 megahertz channels, you'd be at 650 megabit data rate. If you could use 160 megahertz channel, you could get up to 1300 data rate. So anyway, you combine those three together to tell you what the your maximum data rate is. Obviously, when you're looking at data sheets and things like that, we assume the most optimistic scenario: the maximum streams the device supports, the maximum QAM the device supports, the maximum bandwidth the device supports. But realistically, in the real world, a lot of your devices are not going to be able to achieve the maximum. So they're going to drop down somewhere over here. So just one more thing, which can confuse things when you're doing throughput testing. Which of these three things is the one that's affecting your throughput speed or your connected data rate? So another question we get a lot is, how many devices can I stick on one access point? And what I can tell you right now is don't pay any attention to what's on the data sheet. And the reason for that is really simple. How Okay, can anyone hear me now? Okay, okay. So I don't know how long the audio had been cut off. So anyway, we were talking here. Okay, 2 to 3 minutes. So we've been talking about this here. Basically, short version, the number of users you see on the data sheet is just how much memory that device has, how many associations it can take. In the real world, you're not going to get anywhere close to that before the Wi-Fi performance becomes so bad everybody's complaining. So it doesn't matter what's on those data sheets, 90% of the time. I guess if something's really cheap, maybe it'll become an issue. But in general, it doesn't matter how many users the data sheet says. Don't use it for planning. Don't use it for comparing devices together. So here we go with a real world sort of example here. In this scenario, we've got an access point that can support at least 3 spatial streams. And we've got users who are trying to watch a video stream that's encoded at 3 megabits per second. So in the first example there, whoops, there we go. You can fit 34 laptops on there, each holding this 3 megabit stream before you run into any issues. Now you'll notice the airtime utilization is only 77%. And that's because before Wi-Fi 6, determining whose turn it is to transmit, is based on that weird sort of listen and then, take a guess type thing. So because of that, as you add a lot of users onto the network, airtime utilization generally isn't, anywhere close to 100%. With Wi-Fi 6 and Wi-Fi 6 clients, you can get really close to 100% airtime utilization. But in general, especially with 11AC and older technology, this is what you're going to see. You're going to see somewhere between, 75 and 80% airtime utilization on a crowded network. So now we change it. We go to a device that only supports 2 spatial streams. And you see, again, the only thing that has changed is how many spatial streams the devices support. And now you can only get 21 users on there before you start running into issues. Take away one of the spatial streams, and now you can only get 10 devices on that network before you start running into issues. So look here at the aggregated throughput, right? With 1 spatial stream support, aggregated throughput of all of your users on that network is only 30 megabits per second. But we know the network can support up to 100 without any issues. But because of the airtime utilization and use of the spatial streams, the number of devices that you can get on there is actually less doing that same application. So it makes it really, really hard to be able to say with any certainty how many different users you can get on there. And that's why if you come to us and you say, well, how many access points do I need? We are going to ask you, well, how many users are you going to have in general? But we also need to ask you, what are you doing? What are those users doing? So in this case, they're watching a fairly high bit rate video stream. Like a 720p YouTube stream, I think is roughly around 3 megabits. So that's going to affect things, but also surprisingly, something like voice over Wi-Fi is also going to be a huge deal breaker. It's not using a lot of airtime, but the problem with voice over Wi-Fi is it has to be real time. Whereas when you're watching a stream from YouTube or Netflix, you can buffer the data. So when you click play, you're actually downloading more than you can watch, and they create this buffer. So if packets come in out of order, which is very common in Wi-Fi, they can then be, grouped up together, get put in place in order before it's your turn to actually play them. But when you're talking to somebody, you can't do that, right? You get these delays and it becomes really hard to have a two-way conversation. You keep talking over each other. So you can't have buffers. So then you also have issues with packet drops. If the packets come in out of order, or the packets get dropped entirely, you don't have time to retransmit them. So that's why when you have a bad connection and you're talking to somebody, you'll sometimes get those drops where you just hear like just part of what they're saying. So because of that, even though voice doesn't use a lot of throughput, and your access point can support a ridiculous amount of throughput, you actually oftentimes are limited to something around 16 users using voice over Wi-Fi before you start running into problems and bad call connectivity. So just stuff to think. It's not a simple answer. There is no simple answer. It really depends on, the client devices themselves, the RF environment, and just what the application is that you're trying to support. So I hope that makes some sense to you. But if there's one takeaway here, it's, just ignore what the data sheets say when it comes to maximum users. It's just based on a theoretical maximum based on how much memory they have to store associations. It has nothing to do with actual performance. What's going to determine actual performance is the Wi-Fi standard itself that the device supports and what those users are doing. So today we've spent a lot of time talking about co-channel interference. So just as a quick summary, basically anytime you have multiple devices transmitting at the same time on the same channel or the same frequency, you run into these interference issues where it becomes hard to hear what it is you want to hear versus the noise that you're getting. So it can be coming from other access points in the vicinity, but it can be coming from anything that's putting out RF on the frequency you're using. So traditionally, the way you have dealt with that is specifically when dealing with co-channel interference from different access points, right? You're deploying an office out there, you're putting an access point every, 30, 50 feet, every other room, whatever it happens to be, and you're getting co-channel interference. The way you solve that was by reducing the output power on the access point. As we talked about earlier, that signal from that AP can travel really far, but the client devices it's connecting to are probably much less powerful. So they're probably much closer into where the access point is. The signal doesn't need to go as far in theory. So you can reduce the signal from the APs and get it closer to matching what the client devices are. And this absolutely will reduce co-channel interference. The problem with doing this is it also reduces your signal to noise ratio. So you're trading off interference related issues with signal to noise related issues, which may cause your clients to connect at lower data rates to deal with that. So our solution for it is something we call smart antenna. If you've ever sold Ruckus, they use smart antenna. Basically, it's us and Ruckus are basically the only guys out there using smart antenna. Cisco doesn't use it, Ruckus does, or HP doesn't use it, Ubiquiti doesn't use it. So basically with smart antenna, instead of using this one fixed antenna pattern, which is what the majority of access points do, a smart antenna actually has the ability to use hundreds of different antenna patterns. So it's able to go through those antenna patterns in nearly real time and choose the optimal antenna pattern for each individual client device. Now, our algorithm has specifically been designed to take into account not just where the client device is in relationship to the access point, but also where other sources of noise may be coming from, and tailor the antenna coverage pattern to try to ignore the noise that it doesn't want to hear, boosting the signal to noise ratio for the data it's receiving from the client device. So smart antenna only needs to be implemented at the AP. It doesn't require anything special from the client device. It'll work with any client device, and it works with moving devices. So unlike beamforming, which really doesn't work too well if you're moving around, smart antenna is fast enough at optimizing the antenna patterns that it works great with moving devices. So we've got a test scenario here that we put together. In this scenario, this is a hotel room, could be a senior living care center. It could be a series of offices, anywhere where you've got a lot of APs. So first thing to talk about, let's backtrack a little bit. When it comes to hospitality, historically, the way people have provided coverage is you put an access point in the hallway and it covers multiple rooms, at least 4 usually, depending on what the walls are made of. Maybe you could get 8 or something like that. But in the last 5 years, almost everything has been moving to 1 AP per room or 1 AP per every other room. And that's just because as Wi-Fi usage has changed, that putting an access point in the hallway just doesn't work anymore. You get too many users on there. The signal is too weak for a lot of people's cheap tablets that they bring or cheap cell phones. So we have seen this move, and this has been a huge move. Mid-tier hotels and higher And we're now starting to see it trickle into even the low tier hotels going to 1 AP per room. So generally you're putting 1 AP in each room, but the power is a lot less than those ones that you would put outdoors. So the signal doesn't go as far as one in the hallway would have. So in this scenario, this is a hotel, but again, we're seeing the same thing also in other things such as offices. We're seeing this in senior care living centers, apartment buildings, condo buildings, things like that. So it's going to be similar across a lot of different environments. So basically we're using 5 gigahertz channels to give us more channels to use. We are not using DFS channels because of the fact that these are end user devices and a lot of them won't work with DFS. So here we go, but we don't have any rooms directly next to each other using the same channel. In fact, one room is on one floor and we've got 2 other rooms on a different floor spaced apart from each other. So what we've done is we've taken our WAC, I believe this is our NWA 1302, which has now been replaced with the WAC 500 and the NWA 5302. But this NWA 1302 is a wall plate AP. And we compared it to the Ubiquiti UAP ACIW, which is also a wall plate AP. Same form factor, same 11N standard, roughly the same power output. The primary difference between these 2 products is our product has a smart antenna. The Ubiquiti product did not have a smart antenna. And it's the smart antenna that's going to be the main difference here. So you see with just 1 AP operating on that channel, when we have multiple users connected to that AP, we get roughly the same performance. In fact, Ubiquiti slightly beat us, right? They got an aggregated throughput of 406 megabits per second versus our 404. Airtime utilization was roughly the same at 67% airtime utilization. Both of these APs are 11AC devices. But now once you've got 2 APs operating on that same channel, and again, they're not next to each other, you start to see a big difference here. So the aggregated throughput on the Ubiquiti is 555 megabits per second, which is pretty good, right? It's better than the 406 before. But if you look at us, we were able to achieve 785 megabits per second aggregated throughput. Basically, the smart antenna is allowing both APs to communicate at the same time without interfering with each other. In fact, there's very little drop off here as far as that goes. And if you look at theoretical airtime utilization between the 2 devices, we're able to achieve more than the theoretical maximum of 100%. We're able to achieve 31%. So 31% of the time, devices on different APs are transmitting at the same time without interfering with each other. Whereas you see here on the Ubiquiti, they reach 95% airtime utilization. So now we add a 3rd AP using the same channel. And again, none of them are directly next to each other. And you'll see the same thing. We've now got an aggregated throughput of over 300 megabits per second, whereas Ubiquiti is basically where they were with 2. And again, actually Ubiquiti's airtime utilization dropped to 91, where ours went from 131 to 155% airtime utilization. Another key takeaway here is smart antenna is keeping the amount of basically aggregated bandwidth or throughput for each AP roughly the same. So it's very evenly spread across the APs, the maximum aggregated throughput. Where if you look over here at the Ubiquiti, and I'm not picking on Ubiquiti, it's just, they're the same form factor, similar power output, they just don't have smart antenna. You will see 1 AP is hogging a lot more of the airtime than the other 2. So users on this AP are getting a much better experience than users connected to the other 2 APs. So it's some real world differences as far as what you'll see out there and what the benefits are of smart antenna. So it's a really good idea to look for smart antenna products. Obviously, we prefer you buy ours, but Ruckus has them as well. When you're doing anything where you've got a lot of APs in the same area or anywhere you've got a lot of users in the same area. So some alternative solutions here for you that we have if you can't afford smart antennas. Those things are kind of expensive. We also offer on some of our APs something called dual optimized antennas or just dual antennas. And again, basically almost every AP out there has a single fixed antenna array that's optimized for you to mount the antenna on the ceiling directly over the area to be covered. It covers out in roughly a circular pattern from where that AP is. The problem is out in the real world, oftentimes you have to mount these APs on the wall. For whatever reason, you cannot mount it on the ceiling central location. So our APs that offer dual optimized antennas have two sets of antennas for each radio in the device. One antenna is optimized for your traditional ceiling mount. The other one is optimized for wall mounting. So whereas a standard traditional AP is not going to be optimized, it's going to send a lot of the signal into the ceiling, a lot of the signal into the floor. You've now got the flexibility to use one AP for your entire install and be able to change the antenna pattern from ceiling to wall based on where you've installed the device. And that can be changed both with a hardware switch or through software. So now just some general mounting tips. In general, you want to mount the access points above the area to be covered as centrally as possible, and you want it to be within reason as high as possible. And generally the reason for that is because Wi-Fi is going to transmit a further distance and remain cleaner through open air than it is going through obstructions. So if the access point is low, more of the signal, especially from the distant users, is going to have to pass through things like cubicle walls, people, potted plants, things like that, which are going to attenuate the signal. So by keeping it up high, you can get the majority of the signal to avoid those obstacles and travel through clean air where there's going to be a lot less attenuation. Obviously, if you're, installing access points, in a football stadium, maybe that's a little bit too high because the antenna is going to end up covering too large of an area with too many users. But in general, that's a rule for you to follow. Drop ceiling material in general, those typical cheap acoustic tiles that 95% of office buildings have, those do not attenuate the signal that well. So you don't necessarily need to poke a hole in the drop ceiling and mount the access point where everybody can see it. In a lot of cases, you can simply rest the access point on top of that acoustic tile and get great coverage. So obviously those acoustic tiles are held up by little metal T-bars. So you want it to be over the acoustic panel, not the T-bars, since the T-bars are metal and they can do weird things with the RF signal. Now, obviously you need to check whatever the building codes are where you're doing this. Some places you can do this, some places you cannot. Some places, if you are doing that, you need to make sure your access point is plenum rated. In some places, it has to be plenum rated, whether it's above or below the drop ceiling. It just depends whatever your local building codes are. But if you can do it, that is a good way to deploy Wi-Fi without, uglying things up and without your, the person paying for it complaining about holes and wires sticking out and things like that. Now, if you're not, when you're mounting it up on a ceiling, the other thing to keep in mind is other sources of metal. Metal and Wi-Fi don't get along. So if you're mounting it to a physical ceiling and there's ductwork up there, there's pipes, there's conduit, those are going to cause issues. So you may want to lower it down from the ceiling. There are various companies out there that sell basically poles with a flat panel on the bottom with holes on it to give you that distance. So you don't want it in between all of those things. You want to drop it down so it's below as much of the metal as possible. Hotel strategy. As we were talking about before, the traditional way of doing it was umbrella coverage. You mount an access point in a hallway and it radiates out and covers a bunch of different rooms. That worked fine, 10 years ago when it was just business users with wireless devices and they were checking email or browsing Yahoo. These days, people are going to have multiple devices in their room. Especially if they have family members with them. People will have a laptop, they'll have a tablet, they'll have an e-reader, they'll have their phone. But also on top of that, what they're doing is a lot more demanding of airtime, right? They want to stream Netflix, right? Even if you're not trying to stream, a lot of web pages you go to have streaming ads or streaming videos that play in the background to artificially inflate their stream count numbers. So those are all using up a lot of bandwidth, and the umbrella coverage idea starts breaking down really fast in those types of environments. So these days, people are using lower powered access points that go into each room. And again, generally it's one per room, although again, depending on what materials things are made of, you may be able to get away with one every other room. And us and most other vendors make dedicated types of wall plate access points specifically for this use scenario. Just other things, if you're mounting an AP in a guest room, you want a lock, or you want a mounting bracket that sort of locks in place. Um, it doesn't necessarily need to be a key, but just something where it's not obvious how to release the device, because hotel guests will steal anything that is not locked down. Another thing to keep in mind is generally you want to mount something, if you're mounting it up high where it can be seen, is you want a device where you can turn off the LEDs. When people are trying to sleep after a really long trip and they're jet lagged, they don't want a blinking green or yellow light above their head lighting up half the room. And some devices have really bright LEDs, especially when it's dark and you're trying to sleep. We also run into issues with guests being paranoid that the blinking light implies that there's a camera in the device. So getting rid of the blinking light at least helps, especially if you're using sort of round access points. You may mistake it for a smoke detector or something like that. So just things to keep in mind. When it comes to the non-guest room areas, when it comes to, the wider public areas, you basically want to plan for each area individually, right? You basically want to plan for your lobby separate from the hotel bar, separate from the restaurant, separate from the pool, separate from the conference rooms, et cetera. So treat each of those as a different deployment when it comes to planning out how many APs you need. Take into account how many users you expect to realistically be there, using your access points. Most hotels, you have a big lobby, you have a large number of users, but the majority of them are only going to be there temporarily and they're not going to be getting on their laptop. Whereas the area where the continental breakfast is, you may have a lot of business users with their laptops there trying to do business while they eat their morning breakfast. So you may need more coverage there, even though you may have less, actual guests in the area at a time. And it's really true here when it comes to doing load balancing and client steering, that you set up each of these areas individually. We have run into situations where one of our customers is deployed in a hotel and they've put every single AP in that hotel on the same load balancing algorithm as one big giant network. And that tends to cause issues because, if you're in a crowded area like a conference room where you need some load balancing issues, your network may be trying to load balance them onto APs that are in somebody's guest room of 2 floors over. So, group those APs together based on where they are. If you're doing load balancing and client steering, it works much, much better when you do that. And just in general, anywhere where you've got a lot of users simultaneously, or you've got a lot of access points, such as like an expo center, you want to use smart antennas. It makes a world of difference. It costs you more, but boy, I tell you, it saves you on the headaches and user complaints. Schools. So you need to find out really how much online learning is actually being done in the classroom. Some schools are still using books. Maybe the teacher is, getting on the network. There may be some like open periods at the end of the classroom where kids do some open study where they get on the network. There are other classrooms where every kid has got themselves a Chromebook and the teacher is streaming video directly from her desk to every single student's screen. And one of the things that, when it comes to doing video streaming over Wi-Fi is it's not multicast, it is point to point. So now you've got, 15, 20, 30 video streams happening simultaneously. So obviously you need a much more robust network if you're doing that versus if, kids are just, browsing the library and Google or Wikipedia, for a few minutes of a day or whatever during an open study period. So know what they're doing. In general, build towards that. How many students they are and what they're doing. You may need 2 access points per room to be able to support those, the number of users and what they're doing in those rooms. So generally, there should be a different SSID for the teacher versus what the students connect to, and this should be on different VLANs to maintain some separation, to keep teachers' computers from being hacked, to keep students from seeing internal documents, things like that. In general, if you have 20 or more students, you should have 2 access points in the classroom. And if you've got 30 students in the classroom, smart antenna makes a huge difference, especially if they're doing a lot of video streaming in those rooms or screen sharing. So now we'll talk a little bit about Wi-Fi 6. I kind of feel that most of you out there are familiar with it at this point. It has, in theory, been around for 2 or more years. So back in the early days, it was called high efficiency wireless. 802.11ax is the official standard from IEEE, and the Wi-Fi Alliance has rebranded it as Wi-Fi 6. And from just being out there and talking to people, I think that's what most people are using these days, are Wi-Fi 6. Now, the interesting thing here is, of course, is that it's called high efficiency wireless, or it was in the early days. So why is that? So Wi-Fi 6 is the first protocol that's really made a dedicated stab at fixing a lot of the issues that have plagued Wi-Fi up until this point. Airtime utilization, code channel interference, things like that. Wi-Fi 6 has gone to huge steps to try to solve those issues. Now, of course, part of the trick with this is if you've still got legacy devices connected to your Wi-Fi 6 network, you're not going to see the full benefit of Wi-Fi 6. But eventually, everything or nearly everything, especially in a business environment, will support Wi-Fi 6, and that will be a very good day for all of us. But it was designed specifically to solve some of those issues when it comes to high density deployments, right? Those airtime issues, those code channel interference issues are something that is a real pain in those dense environments where you've got a lot of users or a lot of access points in the same area. So you can fit more in the same area, you can fit more users on the same AP. So that's where the high efficiency comes from. It better utilizes the airtime. It's much more efficient. So it's much better for everyone else on there. Now, one of the nice things here with Wi-Fi 6 is it works on 2.4. A lot of people don't realize that when you buy an 11AC access point or router, only the 5 gigahertz radio uses 11AC. The 2.4 radio is still using 11N, right? It's what, almost 10 years ago. So Wi-Fi 6 now can work on both 2.4 and 5 gigahertz. So your 2.4 devices can get a big boost here. And it uses a lot of different technologies here, 1024-bit QAM, OFDMA, uplink Mimo. I go through these more in depth on our Wi-Fi 6 webinar. So if you're interested in learning a little bit more about that and the different technologies individually, I talk a little bit more about them there. So Wi-Fi Alliance started certifying things, I want to say in early 2021, maybe the end of 2020. The interesting thing here is the actual 802.11ax standard wasn't actually certified until Q1 of this year, and the full spec wasn't actually published until May of this year. And despite that, there have been people selling Wi-Fi 6 products for at least 2 years, probably closer to 3 years in some cases. And that's because in the early days, there was enough of the spec out there that you could make a product that implemented some of the Wi-Fi 6 changes. And because there is no Wi-Fi 6 naming police out there, you can call anything you want Wi-Fi 6 just about. And, as long as you've implemented some of the features, is it or is it not Wi-Fi 6? It might be like a certain cellular provider that was advertising their product as 5G, even though it was using LTE technology, the Gen 4. So it's one of those things where it gets kind of muddy at times when looking at products. So anyway, some of the early chips out there supported some features, but not all of the features that really makes Wi-Fi 6 Wi-Fi 6. So it's something to keep in mind. And that's why also you've seen products advertised as Wi-Fi 6 long before the standard was actually officially finalized, as well as just the bureaucracy involved in the IEEE process. For at least the last year or so, maybe a little bit more than a year at this point, enough of the spec was standardized that it was possible to make chips that support the full feature set, with any tweaks done between then and the final version being able to be solved in software. But the older stuff, you cannot. The older stuff, the hardware just doesn't have the horsepower to do it. So that leads me to this slide, when Wi-Fi 6 isn't Wi-Fi 6. And I should say here, we encountered this the same back in the day with 11N versus 11G. Only back then, people were nice enough to advertise these products that only had partial support for the standard as N-Lite. And these products really should be thought about that don't support the standard as Wi-Fi 6 Lite. Unfortunately, people are advertising this as just Wi-Fi 6. So some things to keep in mind here. A lot of the products out there are using this older chipset. Now, it used to be really easy. If the product came out more than 2 or more years ago, you could be guaranteed it was using a Gen 1 chip that's missing some of the key features. Now, one thing to keep in mind here, I've got Qualcomm listed. Broadcom is basically the same. The Broadcom Gen 1 chips, similar list of missing features that are available on the Gen 2 chips, or however you want to name them. So that's something to keep in mind. And like I said, it used to be the older products, but a certain very large network vendor just launched a line of Wi-Fi 6 products that are still using the old Gen 1 chips and are missing some of these key features. And they're not going to tell you that you're missing these key features. You're going to have to look at those data sheets essentially and go through there and say, do they mention upstream OFDMA? Do they mention upstream Mimo? Do they mention TWT? Do they mention BSS coloring? And if they're missing from there, if all of them are missing, you may want to take a closer look and try to find out, are those truly Wi-Fi 6? Because otherwise you're deploying a Wi-Fi 6 product, but you're missing out on the key features that make what Wi-Fi 6 this huge game changer. Something to keep in mind. Another thing is Ubiquity, for instance, their Wi-Fi 6 products only have Wi-Fi 6 on the 5 gigahertz radio. It is still 11N on the 2.4 radio. So that's something else to keep in mind. So when it comes to Zysel, all of our Wi-Fi 6 CPE and NBG routers are the full Wi-Fi 6 Gen 2 chipset. They support all of the key features of Wi-Fi 6. Our business class APs, everything that's 1 series or higher, NWA 110AX, 210AX, 510D, 610D, 650S, they all support the full Gen 2. They support the full Wi-Fi 6 feature set on both radios. Now we are launching here soon a NWA 50AX. It's really not aimed at you guys. We don't really consider it a business access point. We're aiming it at that prosumer space that Ubiquity and TP-Link target on Amazon. And it does not support the full Wi-Fi 6 feature set. It is also missing some of the features you would expect to find on an access point, such as 8021X. So just keep that in mind. We are going to be launching our first AP that does not support the full Wi-Fi 6 feature set. It is the NWA 50AX. In general, I would tell you guys to avoid that. But everything else, everything that qualifies in the partner program, full Wi-Fi 6 feature set. And then I want to talk briefly here about Wi-Fi 6E. You may have heard about this. So basically, the FCC last year decided to open up 6 gigahertz spectrum. So now Wi-Fi can use 2.4, it can use 5 gigahertz, and it can use 6 gigahertz spectrum. And this chunk of 6 gigahertz spectrum is gigantic. So just this alone is going to solve a lot of those code channel interference issues, because so much bandwidth is available, even if you're using 160 megahertz channels. You still can have 7 without having any overlap. It's fantastic. But of course, there are some issues here. First one is obviously as frequency goes up, range goes down. So 6 gigahertz is obviously much higher than 5. So you are going to see lower coverage patterns in 6 versus 5. The other problem is just like where 5 was being used by legacy companies and legacy devices, 6 gigahertz was already being used by people. It was licensed spectrum. You had to have a license to use it. Specifically, 6 gigahertz is being used by a lot of utility companies, and it's being used by news reporters. So in order to solve that and allow everybody to co-work together, instead of DFS, they have something new called automatic frequency control. It should be a much smoother process than DFS is when it encounters legacy devices. There's really nothing out right now that I'm familiar with that really supports Wi-Fi 6E, but it is coming. I think there is stuff that's going to ship here soon from some vendors. We do not know when we are going to launch the product. Zysel will be launching Wi-Fi 6E. Right now, it really depends on the chips. The first generation of Wi-Fi 6E chips don't support some of the features that all of the rest of our access points support. So we are waiting for future generations of the chip, 1.1, 1.2, something like that,
which are able to support the full standard feature set that you find in all of our business class APs. We don't want to launch this and have it missing some features. It just causes confusion. So once those chips are available, we will launch a Wi-Fi 6E product. We had originally hoped that that would be this fall. Unfortunately, I'm sure all of you are aware, there are huge issues with chipset supply, and because of that, the chipset vendors have put more focus on supplying existing product than developing and solving some of these issues on the new chips. So it's been pushed back a bit, but it will be coming. So that is what Wi-Fi 6E is. And when it does come out, one thing to look at is there will be both devices that are dual radio and devices that are tri-radio. So tri-radio would be able to support 2.4, 5, and 6 simultaneously on the same access point. Whereas those dual radio ones, you'll have to choose which of those 3 spectrums you want to use at a time. So that's it for today's webinar, guys. Again, I apologize for the dropout there when my connection went down. I have been asked just to share with you guys, most of our webinars are recorded, and then within a day or two of the webinar, they are published there on our YouTube page. So if you miss something or there's somebody at your office that you think should watch it, you don't have to wait a month for us to do the webinar again. You can always watch a recording of it. If you had to drop out and miss part of today's, you can catch it, again later. Or I have done this webinar before, so you can always watch an older one. There hasn't been much change, always little updates in there, but it's out there for you. And then I've also just wanted to point you to our LinkedIn. Feel free to connect with us there. So on YouTube, we are known as Zysel America Channel. There are lots of different Zysel channels on there. So Zysel America Channel is what you want. And on LinkedIn, we are Zysel-US-channel. Although I think if you just put that in without the dashes, you'll be fine. So again, if you have any questions, send them in using the Q&A window. I know we went over a lot of dry, boring stuff, and I know I'm not always the best at explaining things, so feel free to send in those questions. And while I'm waiting for questions to come in, I have none of them waiting for me currently. Feel free to check out our forum. We have a user forum. I know just about everybody does these days. One of the nice things about our forum is it is used by our R&D and our product management team back at our headquarters. They absolutely do monitor that, and occasionally they will weigh in and respond to somebody, but even if they don't respond to you, they will see the feedback you are giving. So it's a great way to be able to voice your thoughts and have them seen directly by those people. It's also where all of our announcements go first. So if we're announcing a new product or a new feature, it will be posted on there. If we have a security flaw, it will be posted on there. So it's a great place to keep an eye on when it comes to announcements of what's changing, what's going on there. And then, of course, my email is up there on the screen, Sean R. Sean is spelled S-H-A-W-N at Zysel.com. Feel free to email me offline. I don't have any questions coming in through the Q&A box. So I'm going to go ahead and end today's webinar. If you do have something you want to ask me, feel free to email me directly or reach out to your sales rep, Jacob, David, Andy, whoever it happens to be, and send them your question, and they'll make sure I see it and respond to it. So thanks, guys. I appreciate you turning out today. Thank you.